Hi everyone. Today I'm going to talk to you about learning sequences of approximations for hierarchical motion planning. So the motivation for this work is high-dimensional motion planning problems. These problems can be hard because you might need to explore many states or because you can get stuck in narrow passages and obstacles. So hierarchical planning is a usual way to deal with this issue, and how it works is that you solve an approximate problem first, and then use the solution of that problem to guide the planner on solving the original problem. Of course, currently the process of designing these approximations and these hierarchies is manual, and this is the thing we're going to try and address in this paper. Here are some examples of manually designed hierarchies. They can get very specialized. So for example, for a legged robot as a quadruped, some people suggest that you should use first a circumscribed cylinder model of the robot and then an inscribed cylinder model of the robot if the first model fails, and then you use a full box model of the robot. Other people have proposed methods where you plan first with only a few links of the robot, and then if you get a plan for that, you use that solution to find a solution where other links are considered as well. Then there are other methods where, for example, you sample spheres along the environment and then try to bias the sampling on full state space to those spheres. So again, designing a planning hierarchy is an ad hoc process. It might need intuition that might be difficult to get for a certain problem. So you have to think about what kind of problem simplifications you should consider, and when several exist, in which order they should be used. So in this paper, we're going to show you how we can discover hierarchical planners automatically. So how we can actually compute multiple problem approximations automatically and learn the best sequences of approximations to use in a hierarchical planner. And we're actually going to obtain multiple solutions, so multiple sequences of approximations, in a way that makes you be able to control computation time or the optimality of your solutions. So here's an overview of our method. So the method starts from a factored state space. Imagine position and rotation, and the collision geometry for your full space. Then we go from this into a graph representation of hierarchical planning for this space. This graph representation looks more or less like this. You start from having a plan in no space, and then you can either plan directly in the full space, or you can first plan in position space and then position plus rotation space. So then we will add parameters to these edges, and we're going to optimize those edge parameters in a training set of motion planning problems. So that is going to give us multiple solutions for these edge parameters on a Pareto front. Each of those solutions is going to have an optimal trade-off between total computation time of the planning hierarchy and motion cost of the final solution. So let me go step by step on how we do this. So we start from a factored state space and a collision geometry. Since the space is factored, we obtain problem approximations by dropping some of the factors of those spaces. And then in order to obtain the collision geometry for a subspace, what we do is that we sample states on the dropped components of a space and then intersect the geometries at those samples to obtain a new collision geometry for this state. So then solving a motion planning problem in each of these state spaces can be done using an off-the-shelf planner. So you plan on this space using the computed collision geometry, and you could use A star or RT or your preferred planning method. So then we represent hierarchical planning as a graph using STDAGs. Again, you start from having no plan at all to having a plan in a subspace and then having a plan in a larger space. So each space that is a subspace of another space has an edge between them. Then we add edge parameters to this graph, and these edge parameters are of two kinds. So one is an edge cost. Edge costs will introduce an order to the approximations. So if you compute the shortest paths on the graph, the first shortest path is going to be the sequence of approximations you try first. So for example, first you will try to plan in the full space. If that doesn't work, then you recompute the next shortest path, and that is going to be the next sequence of approximations that you're going to use. So then the other parameter is computation time budgets for planning in each of these subspaces. So this is going to be useful when you use anytime planners. So you could decide, for example, to try for a short time budget to compute in a full space, and if that doesn't work, you can try longer using a traditional hierarchy. Then the next step is to learn which values to choose for these C's and T's. So we're going to learn which C's and T's to perform best on a training set of planning problems. We're actually going to estimate the Pareto front between the total computation time to arrive at the solution and the final motion cost. So here's the first scenario in which we evaluated this method. So here's a robot, and the planning space is position, pitch rotation, yaw rotation, and the mode. This mode is choice of controller. So for example, a walking controller, trotting controller. This robot can move in different ways, and each of these controllers has different cost functions. So this leads us to automatically generating this graph of possible sequences of approximations, and then we estimate the Pareto optimal C's and T's that we put on these edges. And this is optimized in a set of 6 motion planning problems, which are on this 3D scenario with different start and goal positions. In our paper, we show that this method leads to slightly better performance than the best performing manually designed hierarchies or serial hierarchies. So you see here different hierarchies have different trade-offs between computation time and final cost, and ours is above all the other ones and can reach slightly lower computation times and lower costs than the other hierarchies. We also compare it to a stronger baseline, which is a state-of-the-art method, and we show that our method can achieve much faster planning than that. So here are a few examples. So if you look at this extreme of the Pareto curve, what our method finds is a strategy where first you try and compute a plan very quickly in the full space, and if that fails, you're going to try to plan a position for the robot and then use that to compute the final plan. On the other extreme, to have a very, very low cost plans, the strategy that our method finds is to, from the beginning, already consider the modes of your robot, which is going to influence the cost. So first you obtain a plan in this space, and then you include also rotation considerations. And if that fails, you're still going to try to compute only position and mode, but always starting with modes, and use that to initialize a plan in the full space. So you can see that you obtain different kinds of hierarchies depending on whether you want to prioritize computation time or cost. We also do another scenario with a different kind of robot and different kinds of approximations to show that our method does better than very specialized hierarchies developed for legged robots. So on the paper, you can also see how our method generalizes better to unseen problems, but the conclusion is that we can find various hierarchies automatically, and that we have an intuitive way to control the trade-off between optimality and the speed of the planner. Basically, you just pick a solution from the Pareto, and then you can choose how fast your planner is going to be. And our hierarchies are better than the best manually designed hierarchies, which could have big impacts in the way we design hierarchical planners. So as part of future work, what is missing? So we should go into more general hierarchies. So currently we just explore approximations by dropping factors in a factored state space. So it would be interesting to go into more general state space projections, or gradually refining discretizations of the same state space, which is currently not possible. Another problem currently is that the parameterization of the sequencing of approximations is discontinuous. So there are some ideas that we could probably borrow from neural network architecture search that would be useful here. So thank you very much for your attention. I'm looking forward to your questions.